All right, let's talk about taking your matrix solving skills and giving them a serious upgrade. We're going to move past just getting a matrix close to solved and learn a technique where the final answer just appears. No extra messy algebra. Let's dive in.
You know that feeling, right? You've done all the hard work, you've gotten all your zeros in the right place, you have this beautiful row echelon form, and you still have to do a bunch of tedious algebra to actually find x, y, and z. Well, we're going to make that final step a thing of the past.
So here's the game plan for today. We'll start with the method we already know and see why it's good but not perfect. Then we'll define our new goal, something called RREF. We'll walk through exactly how to do it, step by step, even for those tricky systems with infinite solutions. And finally, we'll talk about a few common mistakes, and then get to the really cool part, why this all matters in the real world. Okay, first things first. Let's give some credit to the method we're building on. Getting a matrix into standard row echelon form is the foundation for literally everything we're about to do. Yeah, using Gauss-Jordan elimination to get that nice staircase of zeros below your pivots, that's a huge deal. It gets the whole system organized and ready to be solved. But it's kind of like getting all the ingredients prepped, but not actually cooking the meal. Today, we're finishing the job. So let's meet our new goal, the absolute, most simplified, perfect form for a matrix. It's called reduced row echelon form, or as we'll call it, RREF. Now, RREF is a bit of a stickler for the rules. It has 3 strict conditions. First, it has to be in regular row echelon form. No problem. But then 2 more things have to be true. Every single pivot must be a perfect one. And, this is the big one, every number above each of those pivots also has to be a 0. So you get these super clean columns with just a single 1 in them. And this right here is why we bother. Look at the matrix on the left, the standard REF. The bottom row says 3y equals 6. Okay, so you got to solve for y, then plug that back into the top row to find x. It's work. But now, look at the RREF matrix on the right. The top row just says x equals 1. The bottom row says y equals 2. Boom. The answers are just sitting there waiting for you. And really, this is the holy grail. When you get the matrix into RREF and you see that beautiful identity matrix on the left, that perfect diagonal of 1s, you are done. The numbers in that last column on the right are your solution, in order, x, y, z. Just read them off. It's that simple.
All right, enough theory. Let's actually do one. It's really just a couple of extra moves once you've already reached row echelon form.
We'll start with a simple one that's already in RF. Our mission is to take it all the way. We've basically got 2 jobs to do. First, make sure our pivots are all 1s. Then, we work our way up, clearing out any numbers that are sitting above those pivots. Okay, so here's where we're starting. See that pivot in the second row? It's a 3. The RREF rules say that's a no-go. It has to be a 1. So our first move is easy. We're just going to multiply that entire second row by a third. That turns the 3 into a 1, and the 6 becomes a 2. Simple enough? Great. Our pivot is now a 1, but we're not done yet. Look at that 2 sitting right above our new pivot. That has to go. And how do we do it? We use the pivot we just made. We're going to take row 1 and subtract 2 times row 2 from it. This is the signature Gauss-Jordan move, using the rows below to clean up the columns above. And look at that. After that one operation, we have the identity matrix on the left. We can literally just read the answer. Top row, x equals 1. Bottom row, y equals 2. Done. No back substitution, no fuss. That's the power of RREF. Okay, but what about those weird cases? What happens when you don't have one single unique solution? Well, RREF handles this perfectly with something called a free variable. Here's the rule of thumb. Once you get your matrix all the way to RREF, you just scan your columns on the left. If you find a column that doesn't have a pivot, that doesn't have a leading 1 in it, then the variable for that column is free. It means it can be anything it wants to be, so we give it a placeholder, usually the letter T, to show that it has infinite options. Check out this example. It's already in RREF. Now let's scan. Column 1, that's our X column. It's got a pivot. Good. Column 3, our Z column, has a pivot. Great. But look at column 2, the Y column. There's no pivot there. That is our signal. That tells us Y is a free variable. So what do? It's pretty straightforward. We just declare lit y equal t. Now we just read the equations off our matrix like before. The bottom row says z equals 2. No problem. The top row says x plus 2y equals 0. Well, since we decided y is t, that really says x plus 2t equals 0. A little rearranging, and you get x equals negative 2t. And there it is, a perfect little formula that describes every single one of the infinite solutions.
Okay, let's bring it home. We'll look at a few common traps people fall into, and then we'll get to the coolest part, why this method is way more than just a trick for your math class.
Here are the big 3 mistakes to watch out for. Number 1, stopping too early. If you find yourself doing back substitution, you didn't get to RREF. Go all the way. Number 2, missing a free variable. Always scan your final columns. If one is missing a pivot, you need a ST. And number 3, forgetting to scale your pivots. They have to be exactly 1. No exceptions.
Now, why does this matter so much? Because this whole idea of getting a matrix into one single, unmistakable final form, that RREF, is exactly what computers need to do incredibly complex things without messing up. Seriously, think about a character in a video game. Every single time it moves, rotates, or gets bigger or smaller, the computer is solving a system of equations. By using Gauss-Jordan Elimination to find the RREF, it gets one single, unique answer for that transformation. It's not just an answer, it is the answer. And that perfect consistency is what prevents glitches and keeps the animation smooth, frame after perfect frame.
So that leaves us with this final thought. The whole point of RREF is to take any messy system and force it into one standard, easy-to-read, canonical form. If having that guaranteed unique answer is the secret to building entire digital worlds, where else could it be the key? What other massive problems in things like coding or network design or even AI are just waiting for us to find their one true canonical solution?